Welcome, everyone. Today, we're unraveling a massive microscopic mystery that fundamentally changed our understanding of the universe. Okay, let's dive into this explainer and look at one of the most famous, absolutely ingenious, and, well, slightly controversial scientific detective stories of all time, the Millikan oil drop experiment. Imagine being handed an impossible task. Like, how do you measure something you literally can't even see? Back at the dawn of the 20th century, this wasn't just some abstract math problem assigned to bored undergrads. No, this was a high-stakes puzzle that completely baffled the world's greatest scientific minds. They knew the electron existed, for sure, but pinning down its exact properties felt kinda like trying to weigh a ghost.
Let's see how this builds across a surprisingly dramatic timeline. In 1897, J.J. Thomson figures out the mass-to-charge ratio of the electron. Fast forward to 1909, and Robert Millikan, along with his PhD student Harvey Fletcher, start their ambitious experiment. By 1913, they publish a definitive paper with undeniable data, and in 1923, this incredible body of work wins Millikan the Nobel Prize in Physics. But the journey between those dates? It was anything but a straight line.
Section 1. The Mystery of the Electron. Pinning down the charge.
To really appreciate the genius of what's coming, we kind of have to put ourselves in the shoes of a physicist back in the late 1890s. So J.J. Thomson had discovered the electron as a particle, and he even successfully measured its mass-to-charge ratio. That was a huge breakthrough. But it was just a ratio. Physicists were desperate to pry that ratio apart into the actual absolute mass and the exact electrical charge. Whoever could figure out a whole new approach to isolate that charge was going to cement their name in history. The race was officially on.
Section 2. Designing the ultimate trap. Catching the electron.
Now, what's really interesting about this setup is how it all came together in a laboratory at the University of Chicago. Physics professor Robert Millikan and his brilliant PhD student Harvey Fletcher designed a mechanical masterpiece. They built a specialized chamber with two parallel brass plates, which is essentially a capacitor. They had a light source shining in, a viewing telescope to watch what was happening inside, and an atomizer at the top to spray droplets into the chamber. I mean, it looks like a complex piece of plumbing, but it was perfectly designed to observe tiny, dancing droplets with absolute precision. Initially, Millikan actually wanted to use clouds of water vapor, but there was a massive flaw. The water evaporated way too quickly to get any precise measurements. Enter Harvey Fletcher with a brilliant aha moment. He went to a local drugstore, bought a regular perfume atomizer, and filled it with watch oil. Unlike water, those tiny droplets of watch oil remained perfectly stable in the chamber. That meant they could make long, careful observations. It was a real game changer.
So here's exactly how this clever trap worked in practice. Step 1. You spray a fine mist of oil into the top of the chamber using that atomizer. Step 2. Shoot X-rays into the chamber to ionize the air, which causes the oil droplets to pick up stray negatively charged electrons. Step 3. Apply a precise voltage to those brass plates. And finally, Step 4. Look through the telescope and observe the terminal velocity of the droplets as they fall and rise.
Section 3. A microscopic tug-of-war. Balancing forces.
Inside that chamber, they weren't just passively watching drops fall. They were observing an epic, invisible battle of fundamental forces. Let's break down that microscopic tug-of-war. Pulling the droplet down is gravity, just the simple weight of the oil. Pushing upward is buoyancy from the displaced air. Opposing the droplet's motion is viscous drag, which acts a lot like air resistance. But the real magic? The electric force. By applying a positive charge to the top plate and a negative charge to the bottom, an upward electric field pushed against the negatively charged droplet. This acted as a direct counterbalance to gravity. So the crucial point is this elegant little equation, QE equals mg. By tweaking the voltage on the plates, Millikan and Fletcher could make the upward electric force exactly equal to the downward gravitational force. The droplet would just stop. It would be suspended perfectly motionless in midair because they already knew the mass, gravity, and the electric field strength. Balancing these forces allowed them to mathematically isolate Q, the exact charge of that single oil droplet.
Imagine being the very first person in history to actually see this work. We actually have Fletcher's first-hand account of that very first trial. He wrote, "As I looked through the telescope, I could see the tiny stream of oil droplets. As soon as I turned on the switch, some of them went slowly up and some went faster down. I was about to scream, as I knew then some were charged negatively and others positively. They could literally freeze a droplet in place. They knew they had done it."
Section 4. Rivalry and the final result. The race for the charge.
Because, science doesn't happen in a vacuum, and the clock was ticking with the international scientific community watching closely. In 1910, a Viennese physicist named Felix Ehrenhoft published findings from a competing experiment, claiming the electron's charge was actually much lower than Millikan's early estimates. This intense rivalry lit a fire under Millikan. He went fiercely back to the lab, ruthlessly refining his apparatus. He even submerged the whole brass chamber in a motor oil bath just to eliminate temperature changes and convection currents. He wanted to gather undeniable, foolproof data that would silence his critics for good.
And the data they published brilliantly illustrates the sheer volume and meticulousness of the work that followed. It was staggering. The comprehensive 1913 data shows observation after observation, plotting the charges calculated from 58 different drops over 60 consecutive days. It proves visually that no matter the size of the drop, the calculated charge always landed exactly on a specific line, showing extreme consistency.
So what was that consistent, fundamental unit they finally found? It was incredibly tiny, approximately 1.602 times 10 to the negative 19th coulombs. Every single drop they measured had a charge that was an exact whole number multiple of this specific value. This was it, the fundamental charge of a single electron.
Section 5. Data and stolen credit. Controversy behind the scenes.
Flawlessly elegant physics is, well, often carried out by flawed humans. And we really have to look at the messy reality behind this pristine scientific achievement. Years later, historians examining Millikan's private lab notebooks discovered a controversy. He explicitly wrote in his 1913 paper that he had reported all the data he collected, but the notebooks revealed he actually omitted certain drops that didn't quite fit his expectations. Now, while this definitely looks like textbook cherry-picking, modern reanalysis by physicists has shown that even if he had included those excluded drops, it wouldn't have significantly changed that final brilliant value. Still, it's a curious smudge on the historical record.
Then there's the whole authorship deal between the professor and his student. Millikan convinced Fletcher to relinquish his name as co-author on that seminal 1913 paper so that Fletcher could use other related work to secure his PhD. It was a complex, highly private arrangement. Millikan got sole credit for the monumental discovery, but he later heavily aided Fletcher's career, helping him secure a prominent position at Bell Labs. And Fletcher? He went on to have an incredibly successful career of his own.
Section 6. Legacy of the fundamental charge. Changing physics forever.
So how do we weigh all that human drama against the lasting scientific impact? Well, despite the behind-the-scenes controversies, the original 1913 Physical Review publication absolutely changed physics forever. It silenced the critics, proved the electron's charge beyond a shadow of a doubt, and ultimately won Robert Millikan the 1923 Nobel Prize. More importantly, it gave the world a vital constant that we desperately needed to understand atomic structure and quantum mechanics.
The ultimate takeaway for us is what this experiment fundamentally proved about our reality. The oil drop experiment proved that electric charge is quantized. It doesn't exist as a continuous flowing smear. It exists only in discrete whole number packets. You can have one electron or two, but never 1.5. The universe operates in exact fundamental units.
Which leads us with a fascinating thought to ponder. If intense human ambition, fierce rivalry, and frankly, a few questionable compromises drove one of the most flawless and important discoveries in physics history, what other foundational truths of our world are hiding behind messy, thoroughly human histories? Thanks for joining me on this explainer, and keep questioning everything.